This video is going to be a solution to this geometrical calculus assignment that we've been working on. So the first thing that we want to do is we want to look at how we're going to plot this function f of x is going to be equal to x squared. So we know this one pretty well. This is just going to be some parabola. So here's the x-axis and the y-axis. This is just going to look like that. Now, the next thing that we want to do is we want to compute the area under the curve from A to B, just some arbitrary A to B. I'm going to assume that these are going to both be greater than x is equal to 0. So here's x is equal to A, and here's x is equal to B. And to find the area under this curve, we know from our calculus classes, we can consider this like a Riemann sum here, where we have this line y is equal to, it's a terrible looking y. So this is going to be y is equal to x squared. And then to find the area under this curve from A to B really means that we're adding up all of these big rectangles like this. And what we're going to do then is say that A, the total area, is going to be equal to the integral from x is equal to A to x is equal to B of x squared dx. Okay. And then from our calculus classes, we know there's some rules that we can apply. This is going to be x cubed over 3, evaluated from x is equal to A to x is equal to B, which is going to be equal to b cubed minus a cubed over 3. But we want to extend the ideas that we were talking about before in the last video for geometrically thinking about calculus in order to cast this rather in terms of some dA is equal to dx dy, and see how this ultimately is going to be exactly the same thing that we have here. So if instead we say that A is equal to the integral of dA, which is going to be equal to the integral of dx dy, really, when we have the product of these two infinitesimals, it's a double integral, because we're integrating twice because we have two infinitesimals. And so what I'm going to do is just to break this apart into the portion where I'm integrating with respect to x, integrating with respect to y. Now, when I'm integrating with respect to y first, y is going to start from 0. So it starts along the y-axis here for y is equal to 0. And then it goes up to the line where y is equal to x squared. And so that's going to be our upper limit here. So this is going to be y is equal to x squared. And then x is going to range from x is equal to A to x is equal to B. And the whole reason why I was doing this was to show you that it gives you the same thing. So when we do this, this first integral here is just going to end up being an x squared. So we have dx times x squared from x is equal to A to x is equal to B. And so this is really exactly the same thing that we have right there. Okay. So this is our problem 1. Now for problem 2, what we want to do is we want to compute the area of a circle of radius capital R using the dA is going to be equal to r dr d theta. And so this is using dA in what's called polar coordinates. So for problem 2, rather than saying dA is equal to dx dy, like we did with the Cartesian coordinate example up here, we're going to say that dA is equal to r dr d theta. And so if we want to find the total area of some circle, so let's make a nice looking circle here. So make a circle here. Okay. So we have, I'll just draw it. So we have a circle. Then really we're talking about these tiny little patches here where one side of it is going to be dr and the other side is going to be r d theta. So that's how we're forming this dA is equal to r dr d theta, because really what this is, instead of dr times, instead of r dr d theta, this r is really multiplying that, and I just kind of rearranged it to collect similar terms. So here what we're going to do is we're going to say that A is going to be equal to the integral of dA, which is the integral of r dr d theta. And again, because we have two infinitesimals, this is really a double integral. So we have some integral with respect to theta, some integral with respect to r. So for our circle, we're going to start from theta is equal to 0, and we're going all the way around this. So we say that this is going to be theta is equal to 0 to theta is equal to 2 pi. And then r is going to start from the origin, and it's going to go all the way out to r is equal to capital R. So this is going to go from r is equal to 0 to r is equal to capital R. And these integrals are pretty straightforward to evaluate. So the first one with r is going to give us an r squared over 2. And then the second one with theta is going to give me a 2 pi. So multiplying those together, we get the familiar relationship that we've seen before for the area of a circle. This just says that a is going to be equal to pi times r squared. So a lot of the point of this assignment was to recover some things that you know from geometry already by going through the specific details for the calculus. So the next one that we have is finding the surface area of a sphere using ds is equal to r squared sine of theta, d theta, d phi. Okay, so we're going to do the surface area of a sphere. So we have, I'm not going to talk in detail about why these are the case. It's not very important, but I'm going to say that ds is going to be equal to r squared sine of theta, d theta, d phi. And here, theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi. And again, I'm not going to go into a lot of details for exactly why these are the case, but we're just going to use this here. So if I want to find the total surface area, this is just going to be the sum of all the little surface areas. So this is going to be r squared sine theta, d theta, d phi, integrated. But we have two integrals, or two infinitesimals, so we integrate twice. This one goes from 0, phi is equal to 0, to phi is equal to 2 pi. This goes from theta is equal to 0 to theta is equal to pi. So when we integrate sine of theta, we're going to get a cosine of theta. Cosine of theta evaluated from theta is equal to 0 to theta is equal to pi. We have our r squared out front. And then from this one, we're just going to get a 2 pi times 2 pi. Okay. Now, looking at this cosine of theta evaluated from 0 to pi, what we end up having is we have cosine. We have cosine. I lost a negative sign here. There should be a negative sign here. So we have a minus cosine of pi. Sorry. I need to play with this because I don't know what these integrals offhand, but I know what the answer is. So I'm just going to play with this for a second. So this is going to be cosine of pi minus cosine of 0. So this one right here, this is -1. This is 1, but we have a negative sign. So this is going to be -1 minus 1 times minus is going to give me 2. Okay. And so then this gives us, again, something that we know, or you might remember, that the surface area of a sphere is going to be equal to 4 pi r squared, where r, capital R, is the radius of the sphere. Now, we're going to do something very similar with the next one. This one's going to be finding the volume of a sphere of radius capital R, with dv is r squared dr sine of theta, d theta, d phi. Okay, so now, instead of talking about a ds, we have a dv, but it's not really that more complicated. So we just have, what number is this? I was on 3, so now this is problem 4. So for problem 4, we want to find some total volume by saying we're going to add up all the little bits of volume, where these little bits of volume are going to come from some r squared dr, some sine of theta, d theta, and then some d phi. Okay, and again, because we have 3 infinitesimals, really we're doing 3 integrals. So we have that integral, that integral. This r for our sphere starts from the origin, so this is going to be r is equal to 0, goes up to the edge of the sphere, which is going to be capital R. Our angle theta goes from theta is equal to 0 to theta is equal to pi. Our angle phi is going to go from 0 to 2 pi. Okay, and so when we do this, first portion right here, this is going to give us an r cubed over 3. And really, the rest of this calculation, this portion right here, is the same as the thing that we had up here, barring the the r squared portion. Okay, so that's really going to just give us a 4 pi. So we're going to get 4 pi here. And so what this says is that the volume of a sphere, again, you might not remember this exactly, but you've probably seen this before. The volume of a sphere is going to be 4/3 pi times r cubed. Okay? All right, so the next one that we have has to do with the surface area and volume of cylinders. So I'm going to kind of just do these sequentially. So this is going to be problem 5 and 6. So for problem 5, we're going to have the surface area of a cylinder, where this is going to be ds is going to be this is going to be 2 pi times r times dz, right? I don't remember exactly how I parameterized this. Okay, so I didn't put in the 2 pi, but the reason why I'm writing that 2 pi already is because I already know when you integrate it out, it's going to be 2 pi. But we'll see why what I wrote here is actually the same thing as what I had in the statement of the problem. So in the statement of the problem, I said that ds is going to be equal to r d theta times dz. And so why are these two things the same? When you integrate over the angle, you get 2 pi. Well, let's see it very explicitly. So s is going to be equal to the integral ds, which is going to be equal to the integral r d theta times dz, and we have some height of h, so z is going to go from 0 to z is equal to h. Theta is going to go from 0 to theta is equal to 2 pi. And so there's that 2 pi factor that I had here. And then when you do this calculation, you end up finding the surface area of a cylinder is going to be the circumference times the height. So this is going to be 2 pi r times h. The last one that we have is just to find what the volume of a cylinder is going to be. This is going to be problem 6. So for problem 6, we're going to say that dV is going to be equal to, this is r dr times d theta times dz. And then if we want the total volume, this is going to be the integral r dr d theta dz. And then we say z is going to go from 0 to z is equal to h. Theta goes from 0 to theta is equal to 2 pi. And then this one is going to go from r is equal to 0 to r is equal to capital R. And when we do this one, what we end up finding is that this is going to be pi times capital R squared times h, okay, as we would expect. Okay, so a couple of quick things to say. I went into a lot of detail for all of the infinitesimals, and so if I was talking about an area, I said it was the product of 2 infinitesimals. So if I have a volume, it's the product of 3 infinitesimals. For our particular cases in this class, all integrals are going to reduce to one-dimensional integrals, so it's not really going to be the case that you're going to be doing something like this. I wouldn't have you do something quite this complicated. Okay, well, that's going to be it. Enjoy.